In mathematics, the finite element method is a numerical technique for finding approximate solutions to boundary value problems for partial differential equations. It uses subdivision of the whole problem domain into simpler parts, called finite elements, and variational methods from the calculus of variations to solve the problem by minimizing an associated error function, analogous to the idea that connecting many tiny straight lines can approximate a larger circle. FEM encompasses methods for connecting many simple element equations over many small subdomains, named finite elements, to approximate a more complex equation over a larger domain. Basic concepts. The subdivision of a whole domain into simpler parts has several advantages: accurate representation of complex geometry, inclusion of dissimilar material properties, easy representation of the total solution, capture of local effects. A typical workout of the method involves dividing the domain of the problem into a collection of subdomains, with each subdomain represented by a set of element equations to the original problem, followed by systematically recombining all sets of element equations into a global system of equations for the final calculation. The global system of equations has known solution techniques, and can be calculated from the initial values of the original problem to obtain a numerical answer. In the first step above, the element equations are simple equations that locally approximate the original complex equations to be studied, where the original equations are often partial differential equations. To explain the approximation in this process, FEM is commonly introduced as a special case of Galerkin method. The process, in mathematical language, is to construct an integral of the inner products of the residual and the weight functions and set the integral to 0. In simple terms, it is a procedure that minimizes the error of approximation by fitting trial functions into the PDE. The residual is the error caused by the trial functions, and the weight functions are polynomial approximation functions that project the residual. The process eliminates all the spatial derivatives from the PDE, thus approximating the PDE locally with a set of algebraic equations for steady-state problems, a set of ordinary differential equations for transient problems. These equation sets are the element equations. They are linear if the underlying PDE is linear, and vice versa. Algebraic equation sets that arise in the steady-state problems are solved using numerical linear algebra methods, while ordinary differential equation sets that arise in the transient problems are solved by numerical integration using standard techniques such as Euler's method or the Runge-Kutta method. In step above, a global system of equations is generated from the element equations through a transformation of coordinates from the subdomain's local nodes to the domain's global nodes. This spatial transformation includes appropriate orientation adjustments is applied in relation to the reference coordinates system. The process is often carried out by FEM software using coordinate data generated from the subdomains. FEM is best understood from its practical application, known as finite element analysis. FEA is applied in engineering as a computational tool for performing engineering analysis. It includes the use of mesh generation techniques for dividing a complex problem into small elements, as well as the use of software program coded with FEM algorithm. In applying FEA, the complex problem is usually a physical system with the underlying physics such as the Euler-Bernoulli beam equation, the heat equation, or the Navier-Stokes equations expressed in either PDE or integral equations. While the divided small elements of the complex problem represent different areas in the physical system, FEA is a good choice for analyzing problems over complicated domains, when the domain changes, when the desired precision varies over the entire domain, or when the solution lacks smoothness. For instance, in a frontal crash simulation it is possible to increase prediction accuracy in important areas like the front of the car and reduce it in its rear. Another example would be in numerical weather prediction. where it is more important to have accurate predictions over developing highly nonlinear phenomena rather than relatively calm areas. History. While it is difficult to quote a date of the invention of the finite element method, the method originated from the need to solve complex elasticity and structural analysis problems in civil and aeronautical engineering. Its development can be traced back to the work by A. Renikoff and R. Courant in China, in the later 1950s and early 1960s, based on the computations of dam constructions. Feng proposed a systematic numerical method for solving partial differential equations. The method was called the finite difference method based on variation principle, which was another independent invention of finite element method. Although the approaches used by these pioneers are different, they share one essential characteristic: mesh discretization of a continuous domain into a set of discrete subdomains, usually called elements. Renikoff's work discretizes the domain by using a lattice analogy, while Courant's approach divides the domain into finite triangular subregions to solve second-order elliptic partial differential equations that arise from the problem of torsion of a cylinder. Courant's contribution was evolutionary, drawing on a large body of earlier results for PDEs developed by Rayleigh, Ritz, and Galercon. The finite element method obtained its real impetus in the 1960s and 1970s by the developments of J. H. Argyros with co-workers at the University of Stuttgart, W. Clough with co-workers at UC Berkeley, C. Zienkiewicz with co-workers Ernest Hinton, Bruce Irons and others at the University of Swansea, Philippe G. Charlotte at the University of Paris 6, and Richard Gallagher with co-workers at Cornell University. Further impetus was provided in these years by available open-source finite element software programs. NASA sponsored the original version of NASTRAN, and UC Berkeley made the finite element program SAP-IV widely available. In Norway, the Ship Classification Society Det Norsk Veritas developed SESAM in 1969 for use in analysis of ships. A rigorous mathematical basis to the finite element method was provided in 1973 with the publication by Strang and Fix. The method has since been generalized for the numerical modeling of physical systems in a wide variety of engineering disciplines, e.g., electromagnetism, heat transfer, and fluid dynamics. Technical discussion. The structure of finite element methods. Finite element methods are numerical methods for approximating the solutions of mathematical problems that are usually formulated so as to precisely state an idea of some aspect of physical reality. A finite element method is characterized by a variational formulation, a discretization strategy, one or more solution algorithms, and post-processing procedures. Examples of variational formulation are the Galerkin method, the discontinuous Galerkin method, mixed methods, etc. Our discretization strategy is understood to mean a clearly defined set of procedures that cover the creation of finite element meshes, the definition of basis function on reference elements, and the mapping of reference elements onto the elements of the mesh. Examples of discretization strategies are the H-version, P-version, HP-version, XFEM, isogeometric analysis, etc. Each discretization strategy has certain advantages and disadvantages. A reasonable criterion in selecting a discretization strategy is to realize nearly optimal performance for the broadest set of mathematical models in a particular model class. There are various numerical solution algorithms that can be classified into two broad categories: direct and iterative solvers. These algorithms are designed to exploit the sparsity of matrices that depend on the choices of variational formulation and discretization strategy. Post-processing procedures are designed for the extraction of the data of interest from a finite element solution. In order to meet the requirements of solution verification, post-processes need to provide for a posteriori error estimation in terms of the quantities of interest. When the errors of approximation are larger than what is considered acceptable, then the discretization has to be changed either by an automated, adaptive process or by action of the analyst. There are some very efficient post-processes that provide for the realization of superconvergence. Illustrative problems P1 and P2. We will illustrate the finite element method using two sample problems from which the general method can be extrapolated. It is assumed that the reader is familiar with calculus and linear algebra. P1 is a one-dimensional problem where is given is an unknown function of and is the second derivative of with respect to. P2 is a two-dimensional problem where is a connected open region in the plane whose boundary is nice and denote the second derivatives with respect to and respectively. The problem P1 can be solved directly by computing antiderivatives. However, this method of solving the boundary value problem works only when there is one spatial dimension and does not generalize to higher dimensional problems or to problems like. For this reason, we will develop the finite element method for P1 and outline its generalization to P2. Our explanation will proceed in two steps, which mirror two essential steps one must take to solve a boundary value problem using the FEM. In the first step, one rephrases the original BVP in its weak form. Little to no computation is usually required for this step. The transformation is done by hand on paper. The second step is the discretization, where the weak form is discretized in a finite-dimensional space. After this second step, we have concrete formulae for a large but finite-dimensional linear problem whose solution will approximately solve the original BVP. This finite-dimensional problem is then implemented on a computer. Weak formulation. The first step is to convert P1 and P2 into their equivalent weak formulations. The weak form of P1 if solves P1, then for any smooth function that satisfies the displacement boundary conditions, i.e., at n, we have conversely, if with satisfies for every smooth function, then one may show that this will solve P1. The proof is easier for twice continuously differentiable, but may be proved in a distributional sense as well. By using integration by parts on the right-hand side, we obtain where we have used the assumption that the weak form of P2 if we integrate by parts using a form of Green's identities, we see that if solves P2, then for any where denotes the gradient and denotes the dot products in the two-dimensional plane, once more can be turned into an inner products on a suitable space if once differentiable functions of that is 0 on. We have also assumed that existence and uniqueness of the solution can also be shown. A proof outline of existence and uniqueness of the solution we can loosely think of to be the absolutely continuous functions of that irritant. Such functions are once differentiable, and it turns out that the symmetric bilinear map then defines an inner product which turns into a Hilbert space. On the other hand, the left-hand side is also an inner product, this time on the LP space. An application of the Rees representation theorem for Hilbert spaces shows that there is a unique solving and therefore P1. This solution is a priori only a member of, but using elliptic regularity, will be smooth if is.